Hi everyone, our project is Food Learning, Food Image Classification. We are group 3 of CS 4641. My name is Victor Stevens and I have worked this semester with Christopher Murray, Joseph Safoy, Jason Pham, and Sahil Sudhir. Food is a vast world and our world can break up food into different cuisine. Food is presentable in millions of ways, but each has their own name to it. In our digitally involving world, most experiences are photo-driven, meaning we have all seen pictures on our Instagram feed, but how can we recognize those food pictures? Basically, the motivation behind this project is to create a food recognition model that does a better job differentiating within various food groups. For example, the pre-trained model had difficulty distinguishing spaghetti bolognese with spaghetti carbonara, like we've shown on the slide. And we would like to modify and improve the classification techniques to resolve this problem. For the data collection process, we have been working with the Food 101 dataset from Kaggle, which is composed of 101,000 labeled images corresponding to 101 different types of food. We wrote multiple scripts in order to split the data into 75% training, 20% testing, and 5% validation sets. The pre-processing of our data is handled through PyTorch's data transforms. The next step was basically to resize the images so that we can pass them into the two models that we are using, which are AlexNet and Inception v3. Then we normalized our images based on the mean and standard deviation of the dataset. Now let's go over the methods that allowed us to approach this project. In order to improve the previously found results, we decided to implement a new technique called squeeze and excitation. We will abbreviate it as SE during this video. This technique is one of many different ways that an attention mechanism can be added to a model. The purpose of the attention mechanism is to help the model produce more informative feature maps by focusing on the channels that are most important before performing classification. Our goal was basically to boost the model's performance by modifying the architecture of the pre-trained model to include the SE blocks. After a couple hours of training, we can go over the result. We have trained multiple models. We'll go over each one of them. The first model that we trained was AlexNet with SE. When we implemented this architecture and began training it, the performance was very bad. We later discovered that this was a result of the optimizer that we were using. However, we did not revisit this architecture with the new optimizer. As you can see in the plots on the slide, the model did not respond well to training. The next model we trained was AlexNet without the SE blocks. This model was trained with the SGD optimizer instead of the Atom optimizer, which actually made a big difference in our results. As you can see in the plots on the slide, the model's performance improved dramatically in just a few epochs. But however, we quickly reached a plateau. We trained this model for 43 epochs and tried to squeeze as much performance of it as we could. However, we stayed mindful of the possibility of overfitting. After trying out a few different hyperparameters configuration, we could not get the model to avoid this plateau. So we decided in the end to move on to a different architecture. The next model we trained was actually Inception v3 without SE. This model performed much better than AlexNet and only required a few epochs in order to improve the performance. However, this model also quickly reached a plateau, as you can see on the slide. And the performance actually got worse after 6 epochs. In the plot, you can actually see the best performance. This is the best performance we've achieved with this model during training. The final model that we trained actually was Inception v3 with SE. This model was by far the best model out of all of them. Because we were focusing on the use of SE for this project, we put a lot of time into trying to optimize the performance of this model. It took a long time to train compared to our AlexNet models, but we were able to get a decent performance with the 14 epochs training sessions that you can see in the plot. An important thing to notice here is that we still ultimately reached a plateau with this model, just like we did with all the others. Finally, after training all these various models, we computed the top 1, top 5, and top 10 accuracy scores on the test set for each of our 3 best performing models. As you can see in the table, Inception V3 with SE performed the best out of all of them, although it did not improve too much on the Inception V3 without SE. It is difficult to say whether or not the SE block helped improve the performance or not. However, in conclusion, the models we trained for this project did not perform as well as we hoped they would. Future work that could be done to improve on this might include trying different architecture, adjusting the number of SE blocks or their placement within the architecture of the model, maybe training more layers of the network, or trying out a different attention mechanism. Despite everything, we didn't achieve the result that we wanted, but our team felt like we learned a lot about deep learning and image classification over the course of the semester. Thank you for listening.